Hello, and welcome to Chapter 8. Isn't it great? We're going to start with dealing with sampling methods, and the central limit theorem. Yes, you're having a theorem. It sounds great. It's not a serum, but it's a theorem. Hi. Again, this is your hostess with the mostest, Professor Naragon, bringing you all this fun stuff with another great installment of business statistics. So, as we know, we have our learning objectives. So, first one, we're going to explain why populations are sampled and describe 4 methods to sample a population. We're going to look at defining a sampling error, explain the sampling distribution of the sample mean, explain how the central limit theorem applies to the sample distribution of the sample mean, and apply the central limit theorem to calculate probabilities. Yeah, only 5 learning objectives. That's great. So, reasons for sampling a population. Now, one, to contact the whole population would be very time consuming. That is always key there. Sometimes they're taking the whole United States, they're taking this whole area, and if you want to try to actually contact each one, it's going to be like good luck. So we will sample, and what we do is use the different methods to help calculate probably a good estimate of what overall the population would. This is where you get a lot of polling from, like with political and stuff like that. The cost of studying all the items in populations may be prohibited. That's a good accounting thing. Cost benefit. Really actually be beneficial to have the cost of doing these studies. If I can just sample, do a small one that gives me, again, an overall estimate of what's going on. The physical impossibility of checking all items in the population. And the destructive nature of some tests. I like how they go destructive nature. Which really is. Again, we're looking at these huge populations, and it just really isn't feasible for us to contact all of them, and we still want to just make it kind of where we can estimate properly. So, we do have some methods that we do this with. First off, we have the simple random sample, which is a sample selected so that each item or person in the population has the same probability or change of being selected. It's also known as cold calling, if we're calling people. But yes, you're going to see this kind of a bit more. Sometimes a lot of studies do random ones. But we have also systematic random sampling, where a random starting point is selected, and then every basically nth member of the population is selected. So we actually create a system and go, okay, so from right here at this point, every 5th person or 100th person in our population size is going to get pulled. Yeah. We have the stratified random sample. A population is divided into subgroups called strata, and a sample is selected from each stratum. So, that one is basically as simple as going, hey, let's take our overall population, and now let's sub it into the heights, or the bayou, or different places, and go, okay, now this is my sample here, this is my sample here. It's also very good comparative sampling. Cluster sampling. A population is divided into clusters using natural occurring geographic or other boundaries. This cluster is also randomly selected, and a sample is collected by randomly selecting from each cluster. Yeah. Similar to the strata group, stratified random sampling, this one will take natural resources like the Rocky Mountains, how we got West Coast, the Plains, and then East Coast, how they're usually separated by mountain ranges. We can cluster the U.S. into those areas, and then again, randomly selecting from those clusters. And now, we get to have some fun. So, simple random sampling is, again, the most widely used method of sampling is a simple random sample. Yeah. It is mostly widely used. It's the easiest, to be honest. We just draw names out of a hat and go, hey, answer me these questions. It's really it. Everybody has the same probability of actually getting pulled. So it's an unbiased sample. That's the one. Another big key, especially when someone's trying to test your population and everything. Again, you didn't skew it one way. Because it's easy to skew when we're clustering or stratification, those kind of things. So, if the population is relatively small, again, one could place all the items of interest, say names, in a box and select the sample. For large samples like the one that we're about to show, this is very time consuming. So, yay! So here, we're going to use a table of random numbers. It's just one of those ways to actually help us out. So suppose the population of interest is the 750 Major League Baseball players on the active rosters. Of the 30 teams at the end of the last season, a committee of 10 players is to be formed to study the issue of concussions. To make sure every player has an equal chance of being selected, use a table of random numbers. So, we're going to prepare a list of all the players and numbers, them 1 through 750. Randomly pick a starting place in the random number table and select 10 three-digit numbers between 1 and 750. Basically, again, the random. Sounds a lot like the systematic random, okay? But this is how we bridge the gaps between the two. So, this example does show how to select random numbers using a portion of a random number table. To choose a starting point, you could choose basically, you can close your eyes and simply point at a number in the table, or throw darts if it's on a dartboard. I always love those. Say, what should we watch today? Woo. But another way is to randomly pick a column and row. Supposedly the time is 3:04. Go to the column 3 and down to row 4. Here's the number is 03759. So we'll use the first 3 digits in the 5-digit number. To continue selecting, you can move in any direction. In this example, we move right. The next number is 44723. So we choose player 447. The next number is 961 and it is too high, so we skip it and we skip the next number, which is 784 because it also is too high. Then the next number is 18910, so we select player 189. And so on until we have a list of 10 players. Okay? So again, nice fun random number table. So, to systematic random sampling. If you do not have a list of the entire population to begin with, you can use the systematic one, which again is taking a random starting point and then every nth number of the population selected. Best examples that we can get is Stud's grocery store wants to study the length of time customer spends in their store. Randomly select the days of the week, the times, and the starting point of the study. Then systematically select the customers and measure the time each spends in the store. Basically, that's it. We always pick certain times, and then we just select that customer, like every 10th customer, or 25th, or 35th, till we reach the number that we need. All right. Stratified random sampling. When the population can be divided into groups based on some characteristic, use our stratified. Again, we want to divide in a subgroup. Examples that we can see here is a study of 50 of the 352 largest U.S. firms' ad spending. Begin by identifying the strata, then use random sampling within each group based on relative frequencies. Frequencies, yes, they're back. So, again, they had 5 stratums. They took 30% and over, 20 up to 30, 10 up to 20, 0 up to 10, and have a deficit. They found the number of firms, and then they just basically randomly sampled. So, a lot of times they basically, based on probability, one firm or 0.02 times 50, basically about 20% chance because we're dealing with 5 and have 50 of the firms, should be randomly selected from stratum 1. We would randomly select 5 or 10% of 50 firms from strata 2. In each case, the number of firms sampled from each stratum is proportional to the stratum's relative frequency in the population. Stratified sampling has the advantage, in some cases, of more accurately reflecting the characteristics of the population than does our simple random and systematic random sampling. Cluster sampling. Cluster sampling in itself is a common type of sampling used to reduce the cost of sampling over large geographic areas. Again, natural boundaries. Suppose we wish to sample residents of the 12 counties in the greater Chicago area about their view on government policy. Well, we randomly select 3 counties and then select a random sample of the residents in each of those 3 counties. That's really all you're doing. Again, this is a lot more, you probably see this a lot more at political polling. Again, when they try to see how a state would swing to one candidate over another. In this case, they're looking at views of government. But we typically will see a lot of this too. Now, with all this sampling, because it's not the full population, there is a chance for errors. It is unlikely the mean of a sample will be exactly equal to the mean of the population. That's basically what we're having with this sampling error. The difference between a sample statistic and its corresponding population parameters. Okay, so example, the Foxtrot Inn number of rooms rented in June, the mean number of rooms rented, mu, is 3.13. Now if we take in 3 random samples of size 5, we find the means, our sample mean, which is x bar, of 3.80, 3.40, and 1.80. Okay. The sampling error is the difference between each x bar and mu. So we're looking at from 3.80 minus 3.13, a 0.67 error, sampling error. The 3.4 minus 3.13, we have a 0.27 error. 1.80 to minus 3.13, you have a negative 1.33. Okay? So, sampling errors can be positive or negative. Using the combination formula, we find that there are 142,506 possible samples of size 5 possible within a population of 30 values. If you sum the sampling errors for all 142,506 samples, the result will end up being 0. This is because the sample mean is an unbiased estimator of the population mean. We can expect there to be sampling errors between sample standard deviation and the corresponding population standard deviation as well, which of course in later chapters we're going to be looking more at that sampling error just to show that there is a difference between standard and population. But at times we're going to have to use sample. You just have to use the sample mean or standard deviation. How can we determine how accurate the sample mean is? Well, this is through the sampling distribution of the sample mean, a probability distribution of all possible sample means of a given sample size. So, the mean of the sample mean is exactly equal to the population mean. The dispersion of the sampling distribution of the sample mean is narrower than the population distribution. The sampling distribution of the sample mean tends to become bell-shaped and to approximate the normal probability distribution. This is where z values and t values can come in. So, how can we accurately do this? Well, let's go through an example. We're going to have Tardis Industries has 7 production employees, the population. The hourly earnings of each employee is given in the table. 1. What is the population mean? 2. What is the sampling distribution of the sampling mean for sample of size 2? 3. What is the mean of the sampling distribution? 4. What observations can be made about the population and the sampling distribution? Okay, so we have hourly earnings of the population employees of Tardis Industries from Joe, Sam, Sue, Bob, Billy Bob, so forth and so on. But Jan, Art, and Ted. I think they really kept with the 3 named squad here. Okay. So first off, what does the population mean? What is mu? Well, the sum of all the hourly earnings divided by the number. So 14 plus 14 plus 16 plus 16 plus 14 plus 16 plus 18 divided by our 7 employees. Comes out to about $15.43. Again, if I want to pop out the calculator, I can do it right now. 14 plus 14 plus 16 plus 16 plus 14 plus 16 plus 18 divided by 7. So that's where they get $15.43. Not too bad. Now, what is the sampling distribution of the sampling mean for samples of size 2? Okay, So here's all the possible answers. We have 21 samples. As you can see, hourly earnings. We have the sum, and then we have the means. Okay. So we can calculate for each one. Not too bad. What is the mean of the sampling distribution? Okay. Sampling distribution of the sample mean for n equal 2. Now, again, we can sum it all. And they actually have this broken down in frequency. Like 14 has 3, 15 has 9, 16 has 6, 17 had 3 to come out to that 21. Okay? Then they took all the sum of all the sample means and divide by the total number of samples, and they end up coming out to $15.43. So, came out to the same number. I know, that's a little interesting there. Right? What observations can be made about the population and the sampling distribution? Well, the mean of the distribution of the sample mean, $15.43, is equal to the mean of the population. So mu equals of mu x bar. The spread in the distribution of the sample mean is less than the spread of the population values. So again, the shape of the population and the sample distributions are different. As we can see with 14, 16, 18. Here, when we have the 2 together of the 21, notice that it's kind of skewed to the left. And it's almost got a kind of a sharp bell curve trying to start. Okay, so that's one way to look at it. It's one way to do it in a small instance. Again, a larger population, it gets a little bit tougher. So what's this critical limit theorem? Oh, So, critical limit theorem is basically if all samples of a particular size are selected from any population, the sample distribution of the sample mean is approximately a normal distribution. The approximation improves with larger samples. Okay, so the bigger sample we get, the more accurate we end up becoming. So if the population follows a normal probability distribution, then for any sample size, the sampling distribution of the sample mean will also be normal. If the population distribution is symmetrical, you will see the normal shape of the distribution of the sample mean emerge with samples as small as 10. If the distribution is skewed or have thick tails, it may require samples of 30 or more to observe the normality feature. So again, this is a very useful conclusion in statistics, and it's true for all population distributions. This allows us to use the normal probability distribution to create confident intervals for the population mean, which you'll get into in Chapter 9, and perform tests of hypothesis in Chapter 10 and 11. And this is some of what they look like. So populations, we got the U, we got a triangle, a rectangle, downward slope, but as they go, sampling distributions, notice that they start to become symmetrical. They start having bell curves as the larger we get. And eventually, they will be completely a bell curve as we get bigger. Just depends on the sampling size that we have, but usually does end up becoming pretty normal. So, conclusions. The mean of the distribution of sample means will be exactly equal to to the population mean if we select all possible samples of same size from the population. Okay. The standard deviation of the sample distribution of the sample mean is also the standard error of the mean, giving us this lovely formula of standard deviation, basically our sigma, equal to standard deviation divided by our square root of n. Okay. There will be less of this dispersion in the sampling distribution of the sample mean than in the population standard deviation. So, even though we do not select all samples, we can expect the mean of the distribution of the samples to be close to the population mean. If the population standard deviation of sigma, the standard deviation of distribution of sample means is sigma divided by our square root. Note that when the sample size is increased, the standard error of the mean decreases. Okay. So, with our sampling distribution of the mean, sample mean, if the population follows a normal distribution, the sampling distribution of the sample mean will also follow. Okay. Be a normal distribution of samples of any size. If the population is not normally distributed, the sampling distribution of the sample mean will approach a normal one when it at least hits 30. Assume the population standard deviation is known. Again, we're always getting to unknown ones later on in later chapters. Determine the probability that the sample mean falls in a particular region. Use the following formula. Our z-value equals x bar minus mu divided by standard deviation divided by the square root of n, our sample size. Example. So our example here is what the Quality Assurance Department for Cola Inc., which maintains records regarding the amount of cola in its jumbo bottle. The actual amount of cola in each bottle varies a small amount from one bottle to another. Records indicate the amount of cola follow the normal distribution. The mean amount of cola is the bottles is 31.2 ounces. Man, I cannot read right now. And the standard deviation is 0.4 ounces. At 8 a.m. today, the quality technician randomly selected 16 bottles from the filling line. The mean amount was 31.38 ounces. Is this an unlikely result? Is it likely the process is putting too much soda in the bottle? Is the sampling error of 0.18 ounces unusual? Okay. So, they do create a z-value by taking the sample mean of 31.38 minus basically the population mean, or mu, of 31.20. And then divide by 0.4, divided by the square root of 16, which was the sample size. And the standard deviation was the 0.4. Comes out to 1.80. Okay. So the z-value of 180 basically can conclude that it's unlikely there is a less than a 4% chance the process is putting too much soda in the bottles. Okay. So this is really using our z-tables to help us figure out what's going on. Because again, in the tail that's shaded is really only 4%. There, 0.0359. So it's very hard to actually see that it's doing it on purpose, or having too much. All right, Chapter 8, Practice Problems. Woo! Got quite a few of these. So, you know the drill of how this goes. Make sure you pause the video if you're watching the video. Try to do the practice problem and then unpause, and we're going to go through it. Okay? Try your best to do these and see where you're making your mistakes. Question 1. The following is a list of 24 Marco's Pizza stores in Lucas County. The stores are identified by numbering them 00 through 23. Also note is whether the store is corporate owned or manager owned. A sample of 4 locations is to be selected and inspected for customer convenience, safety, cleanness, and other features. There's only one part of this. Here's the second. Here's our questions. The random numbers selected are 08, 18, 11, 54, 02, 41, and 54. Which stores are selected? Well, looking at our chart, starting off with 08, that is 303 Louisiana. Then it jumps to 5155 South Main, then 3501 Monroe, then 2652 West Central. Okay. Now remember, some of these are bigger. We can't use the 54 because there is no 54. Can't use 41, 41, sorry, because again, there's no 41. We can only use 08, 18, 11, and 02. Okay. Use a random number table, Appendix B4, or statistical software. You can do this on your own. We're not really going to go over it in this video, just because it's going to vary. Not everybody's going to have the same answers. That's a very varying item. Okay. Use systematic random sampling. Every 7th location is selected, starting with the 3rd store in the list. Okay. Which locations will be included in the sample? Okay, so we start with the 3rd. So 630 Dixie Highway is going to be selected. Then go 7. We'll land up at 10 with 835 South McCord Road. Go 7. We'll hit 4624 Woodville Road. And then if you try and go 7 again, you're going right off the list. Okay? So we have 3. And then again, they say use stratified random sampling, select 3 locations. 2 should be corporate owned and 1 should be managing owned. Again, since you're selecting those, that can be varied. All it is grouping and then randomly picking. Nothing we can do right there. Question 7. A population consists of the following 5 values: 12, 12, 14, 15, and 20. Okay? List all samples of size 3 and compute the mean of each sample. Alright. So, for us, we're going to go so we want to list all of them, starting with sample 1, which is 12, 12, 14. We're actually going to make this a little bit bigger. There we go. 2. Will be 12, 12, 15. 3 be 12, 12, 20. 4 1 to be 14, comma 15, comma 20, 5. Actually, to make this a lot easier, let's do it this way. 12, 12, 14, 12, 12, 15, 12, 12, 20, 12, 14, 15, 20. Then we can have 12, 14, 15. Oh. 14, 15. Then we can have 12, 14. 15 again, because we got two 12s. Those two 12s are going to really mess with us. 12, 15, 20, 12, 15, 20, 12, 14, 20, 12, 14, 20. Okay, there's really only 10 possible ways since we're going for 3. So 7, 8, 9, 10. Next, let's go ahead and do the sum. So formulas, auto sum. There is our sums. And let's go ahead and figure out the mean. So this will equal this number divided by 3. Okay, and then we're going to go ahead and form home. Make it about 3 decimal places. All right, so we need to still figure out basically the mean of each of the samples we just did. Okay, so there's the mean of each of the samples. Mean. Okay. B, compute the mean of distribution of sample means and the population mean. Compare the two values. So let's auto sum. Yes, stop doing file. Formulas, auto sum. And we'll take that 146 and divide by 10, since we're dealing with 10 numbers, 14.6. Now, we really only have 5 numbers. We have 12, 12, 14, 15, and 20. So, we can take this, we're going to go equal 12 plus 12 plus 14 plus 15 plus 20. And divide by 5. Notice they are the same. So all the populations will be exactly the same. No worries. It means just our sample size is pretty good. Next, the dispersion of the population is greater than that of the sample mean when we compare the dispersion of the population with that of the sample mean. The sample mean varies from 12.66 to 16.33, whereas the population varies from 12 to 20. Okay, so we had to have a greater distribution. Okay, not too bad. Not too bad. Question 11. All right. Appendix B.4 is a table of random numbers that are uniformly distributed. Hence, each digit from 0 to 9 has the same likelihood of occurrence. In fact, they did a random board right there. Now, they said draw a graph showing the population distribution of random numbers. What does the population mean? Well, right here, we only have really 0 through 9. So the population mean, pop up our calculator, is going to be 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 divided by 10, because we have 10 numbers. So our population mean, or mu, will be 4.5. Okay. Let's go. Following are the first 10 rows of a 5-digit from the random table of random numbers. Assume that these are 10 random samples of 5 values each. Determine the mean of each sample and plot and means on a chart similar to chart 8-4. Compare the means of the sampling distribution of the sampling mean with the population mean. Alright, so with this, so basically all they did was sum up each of these rows. So if we wanted to actually put them all in, we could do the sum. So let's go ahead and bust out Excel. Go ahead and type these in real quick. Oh, a little bit too large. So we had 0 9 5 7 6 1 1 8 0 7 2 4 4 7 1 7 3 7 8 8 7 8 9. Okay, one more row. 1 3 1 0 5 7 8 5 9 4. Okay, so we put in our random numbers. Of course, we're going to do quick sum. Formula, auto sum. Scroll down. Have it automatically calculate because that's what makes it awesome. Alright, now we take and find our mean. Means. So that's going to equal our sum divided by 5. Okay, and then it wants to find the sample means. So we take the sum. It's 48.4. So the sample mean as itself will equal to the 48.4 divided by our number of rows, which makes it 4.84, which is close to our population mean of 4.5. The sample means range from 2.2 to 70, whereas the population value range from 0 to 9. So we can see that sample means tends to cluster between 4 and 5. Again, very close. Again, if you want to find your error, you can take 4.5. So that's the pop. So sampling error would have been these two subtracted. So I'm looking at a sampling error of 0.34. Okay, not too bad. All right. So let's move on to hopefully something that has a little bit of showing you what's going on. All right. So question 15. Our last question has what? 1, 2, 3, 4, 5, 6 parts. Okay. So a normal population has a mean of 60 and a standard deviation of 12. You select random samples of 9. Okay. So apply the central limit theorem to describe the sampling distribution of the sample mean with n equal 9. With the small sample size, what condition is necessary to apply the central limit theorem? Okay. So with our selection right here, we're going to be looking at, let's see, no, we had a formula. Where are you? So here we go. Standard error of the mean. So remember, it's our standard deviation divided by the square root of n. So calculator. Our standard deviation was 12 divided by 9, the square root of 9. So it would be 4. So with the small sample size of 9, the application of central limit theorem requires that the population is normally distributed. Okay. Next, B. What is the standard error of sampling distribution of sample and means? We just did that. That is 4. Not too bad. So again, we do need to have a normal distribution, and our standard error of sampling is 4. What is the probability that the sample mean is greater than 63? All right. So let's go ahead and get our formula for Z. Remember what that was? All the way back here. So it's going to be a sample mean minus mu divided by our sigma divided by square root of n. So right now our sigma square root of n is 4. Makes life a little bit easier. So we take our sample, which is 63, minus 60, divided by 4. We're sitting at 0.75. Okay, so 0.75 is our Z. Sorry. So we need our chart. Alright, so chart right here. So our chart states that we're going to be, our Z value is 0.75. All right, 0.7. There's 5. So it's right there at 0.2734. So for us, we're going to take that, and the probability that the sample mean is going to be greater is, taking our calculator, 0.5 minus 0.2734 will equal 0.2266, or 22%, 23% that the sample mean will be greater than 63. How about if it's less than 56? Okay, so again, we're going to take our sample mean minus our population mean, divided by 4, which is our, again, standard error of sampling, come out to -1. Well, basically it's just going to be 1 for us. So that will lead us to 0.3413. So I remove these older ones. 0.3413. So again, we're going to take from our calculator 0.5 minus 0.3413. Our answer is about 15%, 16%. That could be less than $56. So what is the probability of 56 and 63? Okay, so this is our addition going on. We would need to add 0.2734 plus our 0.3413. Okay, so probability that it's going to be in between those, so now in the tails, is about 61.47%. Okay, F. So again, probability of sample mean between 56 and 63. F, what is the probability that the sampling error, x bar minus mu, would be $9 or more? Okay. That is that the probability that the estimate of the population mean is less than 51 or more than 69. So, to figure this out, we would have to take the z-value of both. Okay, so calculator. Again, take 51 minus 60, divide by 4, 2.25. Okay. And of course, also if you took 69 minus 60, divide by 4. So our z-value is 2.25. So using our z-table, 2.25 okay, 2.2 so it should be right there, 4.4878. So again, checking the chart, yep, 0.05, 2.2, yep, 0.4878. So again, taking 0.5 minus 0.4878 ends up being 0.012. Since we're looking at both tails, it's a two-tail test basically here, we'll multiply it by 2. So we have a 2% chance that the mean will be more than 9. That's it. So that concludes Chapter 8. So if you have any questions whatsoever, please send me an email. Please contact me and we'll go through to help you understand how to handle this sampling and these formulas right here. Okay? For now, I wish y'all adieu, and I will see y'all next time.